resonance and like to how to make sure that you have all the resonance structures and like just more practice on like where to move bonds and unbonding electrons.
Sure, no problem. Hey, Jackie. Yeah, how about, what do you feel, tell me what you feel confident with resonance. And if that's nothing, then that's fine too. I don't want to over explain something if you already kind of understand certain concepts of it. So, radical versus, you know, um, um, pairs of electrons, what, like, how, where do you think you lie on, like, as far as like, I know nothing and I want to practice right from the beginning, or like, I understand, moving towards a positive first, or I understand sp3 hybridized, don't get to participate in resonance. Like, where are you at? Where do you feel like you're at?
Yeah, I know that sp3 doesn't participate in resonance and it's only sp and sp2. um I I guess I'm struggle the most with um identifying which carbons or which atoms are sp2 and sp3. In like a ring I generally get it, but when there's like offshoots, sometimes it's difficult for me to know if it's sp3 or sp2 and whether it's a part of the conjugate structure
Sure.
or if it's not. Also going over and being more confident in like major and minor contributors.
Yeah. Yeah, totally. Okay. So, as far as like, how do you feel about radical versus bonding, or like, or pairs, radicals versus pairs of electrons, or a bond, for example, right? But like, I'm sure can you see my screen? I don't know what you're working with on your side, but can you see my screen?
Yeah.
Okay, so this top example right here is, this is like about a radical. So do you, like, how do radicals feel versus like these we're talking about, like bonded electrons or like pairs of electrons?
Um, it'd be nice to go over.
Sure, everything. Yeah, okay, cool. I just don't want to like overdo something that, I don't want to beat you in the head about something if you already like feel confident with it. So
No, yeah.
let's um let's just start with, as far as like being able to identify if something is sp2, sp3, etc., right? So say we have, I'm just going to make a structure up and hopefully I make it up somewhat okay, right? So in this structure, tell me what this carbon is, what the hybridization of this carbon is.
sp3.
Yep, exactly. So you can always just, oh, that's a light color. You can always just like draw. I always just draw little lines, but I mean, if you want it to be complete, but like, I know what they are for me. So I just try to do things like shorthand. Um, and what about this one?
sp2. I
Yep,
know which
exactly.
ones in this structure are sp2 and
Cool.
sp3.
Okay.
It's mainly like I've seen like an oxygen with a single bond and two pairs of non-bonding electrons bonded to in a hydrogen, and like it's mainly in those scenarios like single and double bonds to oxygen and like in like the main ring between carbons and hydrogens. I know the difference between
Got
sp2
it.
and sp3.
Got it.
um but it gets a little more difficult for me beyond that.
Sure, yeah, okay, so this example right here that I just drew out, this is an alcohol, right? But
Mm-hmm.
and also not like if we were, to draw it correctly, really it would be like this. But so just for corrective sake, let's do this. Okay, so in this case, right, is this like what you were talking about?
Kind of, yeah.
Okay, or were you meaning more of like how this has like a single bond, but it has three. So oxygen's happy to be negative. So oxygen's
Mm-hmm.
happy to have extra electrons. So that's something to keep in mind. Whereas like nitrogen would prefer to be positive. So if you have two structures, like in this one, this is a really great example of that. If you have um two atoms that are in the same structure and one is oxygen, for example, and one is nitrogen, this is going to be a more correct option than if you saw this. Like this would never happen. Oxygen will just take the electrons, right? So, and if you have an oxygen with a positive sign on it, that is going to be such a minor contributor that they would consider it, what do they say, not like it's legal, but
Reasonable.
it's just not, yeah, not reasonable. Thank you. It's just not reasonable. It's never, like almost never going to happen, right? Like it's possible, but just not going to happen.
Yeah.
So that's something to consider. Now if you have like so in this example, right, like we're literally just moving, it's asking like what, like oxygen is sp2 hybridized. It's asking for like if we move these electrons here and we and then this becomes like when then we bump these electrons here, right? Because
Mm-hmm.
nitrogen is going to prefer to be positive over
Mm-hmm.
everything else, right? And so that's why we're going to see these like, like you said with your skeletal structure of like where you have just these like dotted lines right here to represent your resonance, and these are like your deltas, right? Or like your one half negative here, one half negative there, right? Top and bottom.
Mm-hmm.
Um, Now, if you had, is there like, do you have like a particular homework question? I just don't think I have any examples on here with oxygen and nitrogen. I just want to make sure to like address that specifically if that's a question you have. Because all I
Let
have is
me
like a bunch of
look.
carbon examples. Um, but like in this one too, uh, it's that same thing. So you can move in either direction with this. Like this is a linear structure, right? As opposed to a cyclical structure. Um,
Mm-hmm.
in this one, we see that like in this top one here, we see that, let me know if you find a question. I don't want to like make something up and have it like not actually work well. So, but like this one, right? Like this would be our sp3 hybridized. So this is going to be the one that doesn't participate.
Uh-huh.
And it like this carbon here is going to be one that doesn't participate. That's why we have this circle that goes all the way around. And it like major versus minor, right? So like this is an example of like an unreasonable example is like, yeah, you could have these like you could have them go this way, right? And like move stuff around. But because you'd be putting a positive charge at the end at a terminal carbon, it's extremely unstable. Yeah, go downstairs and ask daddy. It's extremely unstable, so you're just not going to see that happen. So that's why they consider
Right.
that like an unreasonable. Um,
Right.
yeah.
And
Um,
then
yeah, go ahead.
if you scroll to the first um problem on here, another question I had is
Mhm.
why is that nitrogen positive? Um, I thought nitrogen only needed three bonds.
It does, and it typically has a lone pair. So remember, nitrogen wants five. So let me just change the color. So you just count lines and dots. So 1, 2, 3, 4, 5 minus 4 equals +1. So that's why it has a positive charge. Same thing here. 1, 2, 3, 4. So same. It does like to be in a bond of 3 like this, but it still wants to have 5 total.
Okay.
Does that make sense?
Yeah.
Whereas like oxygen wants 6, right? So 1, 2, 3, 4, 5, 6. So it's happy. That's why it's at 0. This one, this top oxygen here, 1, 2, 3, 4, 5, 6, 7. So whoops. Oh, I did that. 6 minus 7 equals the -1. So that's why we have this negative charge here. So like a neutral nitrogen would look like that.
Oh, okay.
But because its lone pairs are being exchanged with either this oxygen or this oxygen, so it ends up being like this in a bond over here and a bond over here, right? A resonance structure, we could do dots. That's what makes this become positive.
Okay.
Yeah. Let me see. Yeah, if you're ever unsure, like a great way to start if you're feeling, let me know if you do find an example, a homework example, and I can like put it up on the screen so we could do it together. But
Okay.
if you're ever unsure about like whether or not, excuse me, the hybridization, I always do this, right? This is a carbon, this is a carbon, this is a carbon, right? I don't put circles, but I'm doing it just so that we can see where all the carbons are, because sometimes people forget that this terminal one is still a carbon, right?
Yeah.
So at this carbon wants 4 bonds, right? So this carbon already has 1, 2, so 3, 4, but because it's a double bond, right, that makes this sp2. This carbon, same deal, this has 3, so this has a 4th one. So there's 3 electron domains, so that makes this sp2, but it's got 4 bonds, quote unquote, right? Same thing
Yeah.
here. So 3, it's happy with 1, 2, 3, 4, right? sp2. And we go around
Yeah.
sp2, right? This one, it's only got 2 that are visible, so you know we have to add on our invisible hydrogens, and then we see now that there's actually 4 lines, so now we can identify that this is sp3. So something that I would always do for my exams is like I would literally just go around and do this and be like, okay, this one, okay, that one's got 4, this one's got 1, 2, 3, 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 4. And then it was like easier, and obviously this is like kind of sloppy, but I didn't add the H's because it was just a waste of time in my opinion. I knew what those lines meant. And this was a lot easier for me to be able to identify like, oh, okay, this has got 3 electron domains, perfect. This one's going to contribute. This one's got 4 electron domains. This one's not going to, it's not going to be a part of it, right? So
Yeah.
sometimes that can be a really easy way to like go around and check that out.
Yeah.
Yeah.
For a homework problem,
Yeah.
question number 9 for the cumulative resonance problems.
Okay, hang on 1 second. Let me get there. Cumulative resonance problems, number 9. Let me see, where do I have room? So draw all additional resonance contributors, give the curved arrow that indicates the formal electron movement, excuse me, that generates the additional contributors, indicate the major, give a brief explanation, give the hybridization of the 2 nitrogen atoms. The resonance contributors show that one of the nitrogen atoms carries a partial positive, indicates which one it is. Okay, let me just put my glasses on. I'm like, why can't I see the screen? I don't have my glasses on. Okay, so I'm gonna just draw this out. Oops.
And my main question for this one was why the nitrogen on the left is sp2 and the nitrogen on the right is sp3.
Sure. Hello, Nicola. Welcome. Okay, did I draw that correctly? It looks like I did. Okay. So let me see. So now we are going to do the curved arrow pushing. So let me change colors. Okay. So obviously, just like for thoroughness, this one's not going to participate. This one's not going to participate. This one's not going to. This one's not going to. Right? These are the ones that are not going to participate. This one can participate because it holds a formal positive charge. This is SP3, as with this one, right? So that's why we're going to see, just for thoroughness there, that's why we're going to see those. Okay, so then we'll start off with, so curved arrow pushing here, right? Which will push these up this way towards the formal charge, right? And so then we'll see that. I'm not drawing the whole structure out just to like show you, right? So, and then the formal charge moves over here. Oh no, wait, no, because that, this electron, okay, wait, sorry, hang on. This wouldn't be a double bond. Yeah, wait. Oh, because this would be negative, that's why. But then you're putting them back, or that would be positive, but then you're putting them there. That's why it's not formal charge, sorry. Because this would be, you're taking away the electrons here, so this would be positive, but then you're adding it here. So that's why it wouldn't be. I just did 2 moves. See, that's the other thing. You got to make sure not to do 2 moves at one time. I did that a lot. I did that a lot. That's why. Okay, so you would move this first, right? And then you would have your bonding electrons here. Sorry. But then this would be a positive charge. And then that's why you do want to move towards positive first. So that can be like one of the tricks is, right, not doing too many moves at one time. So if you see a positive charge, do the positive charge first. Move your electrons over to here. That's this one, right? And then we have, and then the positive charge moves here. So then we move it here. Okay. And then when we move that there, then the positive charge would then move over to our nitrogen, right? And then we'd have this double bond here, and nothing over here really has changed. This is still a double bond here with our nitrogen. So, and then what? So then we move, so we can move these here and bump these up here, right? Oh, no, we can't. No, because this wouldn't go anywhere because this is SP3. Just kidding. Okay, so now in these 3, I'm going to show you why. Let me draw my arrows. One is SP2 and one is SP3. Okay, so in these 3, so yeah, so sorry, you're not going to move this here. I didn't draw the bottoms of these structures, but hopefully you guys get that. This structure, I'm just going to skip over this for right now, right? So the main structure that you want to look at is the structure that all 3 have in common. So in this one, oh, they all 3 have hydrogen. Okay. That is a good question because I was going to say, but this one also has its hydrogen. So why would it be sp2? So yeah, so what I was going to say is that you want to look at whatever your main structure is that all, however many resonance structures have in common, right? So let me just finish that sentence. So whatever your main contributors are, or rather whatever your main structure is what you're going to draw as your structure, right? So these are all in all 3, right? So our nitrogen with the 2, these lone pairs, I didn't draw them here because I wasn't working on that, but these have the lone pairs. So this would be your like base structure. And then what you would see is you would go through and say like, where do I see bonds, double bonds that appear through the structure, right? And so that's where you get your dotted line structure. So
Uh-huh.
then this we have bonds not in all of them. I mean, we have lone pairs not in all of them. Okay, there. So that would be where you get that from. And then, but yeah, it carries a partial charge. This one carries a partial charge a third of the time. This one carries, so what we would see is we would see partial charge, partial positive, partial positive. And this obviously is sp3. But it's saying that this one is sp2, that's what you're saying?
Yeah.
It has 3 domains the whole time though. I'm wondering if it's a typo, because that, does it have a video? Let me see. Let me click on solution. Let me see. Did you watch the video?
Yes, I think.
Didn't
I
you?
can't remember. But like looking at the like solution that they have up.
Yeah, that's so weird. Those are all sp2. Okay, wait, let me see what this says. Yeah, because that's so weird. Mm, mm. So, okay, you're probably not going to see something like this on the exam, to be honest, but the reason why they say that is because this nitrogen, because that nitrogen is participating, it's giving up some of its p bond into this resonance structure. And so that's why it's saying that it's sp2, because it's losing part of its pi bond to that. Mm. That's a tricky
But
one, to be honest. I wouldn't have known that without watching that, because it does, I would have assumed also sp3.
but could the N on the right not also?
No, because it's not involved. It's not involved in resonance.
Okay. I guess I
Yeah.
just don't get why it's not involved in resonance.
Because you would end up it's not I guess they consider it like a not a reasonable contributor to put the N like with a positive charge and to move the electrons over to this, like, yes, N will happily be because if you did participate it in resonance, what the structure would end up looking like, I'm just going to draw this one on the right. Wow. I'm just drawing this portion of it, right? Because what would end up happening is you would have, let's see, this bond would go here, and then these electrons would go here because this cannot participate. So it would end up getting stuck on this one here. And this would be negative, and this would be positive. And while nitrogen is happy to be positive, this structure here makes less sense than this structure here. So it's one of those things that's legal but not reasonable, because nitrogen is happy to be positive, but this doesn't really make sense for these non-bonding, like you have 2 charges here versus you have 0 charges here. Does that make sense? So you're always going to have the least amount of formal charge. That's what's going to make a reasonable structure. Like, so if you have 2 structures and one has a 0 net charge, and this one also has a 0 net charge, but this has 2, 0 net charge, but this has 2 formal charges, and this has 0 formal charges, you're going to have the one that has 0 formal charges on it. Does that make sense?
Yeah.
Everybody wants to be like happy and even and equal and neutral and the lowest amount of energy possible. And so though the net charge is still 0 here, it's not the lowest energy possible because of those formal charges.
Right. So then I guess my next question would be is say there's a structure and it has one positive formal charge. If there was a resident structure that was technically possible or legal, but it had a negative charge on it, it would be unreasonable, or I guess like,
Not necessarily. You could still have negative charges. Like, for example, oxygen is a great example. Oxygen is a great example of that because oxygen is happy to have a negative charge. Let me show you. We have up here, for example. These are perfectly reasonable resonance structures and legal or whatever you want to call them. And see, even though they still have these negative charges here.
right.
So
I guess,
yeah, go ahead.
um, like I get that because in both structures there's a positive and a negative. I guess I've just noticed that like when there's a resonance structure that adds an extra formal charge, kind of, um,
So like
does
this one,
that
for
tend to make it
example,
unreasonable?
so like in this one, for example, it might not be unreasonable, it just might be a minor contributor, right? So in this one, for example, there's a negative charge here and there's a negative charge here that wasn't there before, right? So it's kind of just moving the negative charge around so that you see on this end, you see that there's two formal negative charges in the conjugated system, right? Versus these are all partial radicals. And then this one is another example of, and this might actually help to answer your question, right? Is like, this is more because of this thing right here, right? Like you're not gonna see this on a like a first degree, you know, you're not going to see that on a methyl, right? Because that's just not stable. That's why we're not going to participate. That's why this is not going to participate, even though it could, right? But this is like an example of two of where we've added a negative charge to something where like it wouldn't necessarily be there. So this is why we would consider this like unreasonable. But as you can see, we still have those formal charges that are just moving around. So if you're just moving formal charges around,
Yeah,
it's
that's kind of what I
possible.
mean.
Yeah. But if
So
you're
like if moving the formal charge around, I get that like different carbons or whatever can have like you can move the formal charge around, but like there's a structure that requires that
that you
formal
add
positive
a
charge is
formal
moved
charge,
around, but it's required that it's like added a negative or something, like that would be
yeah.
unreasonable.
Yeah,
Okay.
exactly. Yeah, you're not going to see. Yeah, exactly. It might be legal, but it's not, like you said, it's not reasonable because
Okay.
all it's doing is increasing the energy. And like, that's not the point. Like, the point of resonance, right, is like that we're decreasing energy, we're spreading out like these electrons, right? We're moving these electrons around to help stabilize them. So if we're putting more formal charges onto the molecule, that's not really stabilizing the molecule, right?
Yeah.
So that would be like kind of the reasoning behind that.
Okay. Thank you.
Yeah, of course. Um, did you have other questions about resonance? Can we go over how you know where to start resonance? Yeah. Feel free also any of you guys to like hop in. But yeah, so to know where to, let me see, is this all BDE? Yes.
I do have some questions, if you don't mind, about Newman projections.
Yes, and we will, I know, because we didn't get to those last time. So yes, we will do that. So as far as to answer your question, Nicola, about where to start. So a great place to always start is to look for any positive formal charge. If you have a positive formal charge, you're going to want to move towards that. Um, and then after
towards that, or you're moving that charge?
both, you move your electrons towards it, which will then move.
Get rid of the charge.
Yeah, it'll move the formal charge from where you just transferred those electrons. So for example, this is, this is a good example of that, right? Let me just erase some of this stuff here, but we have this, let me just erase some of that, right? So we have this, this is this formal charge. Go. Thank you. We have this formal charge here. And so what they're suggesting, and what I would suggest, right, is that you move this double bond here and you move it into this area. So now we've got this double bond here, but because we took electrons away from this atom, carbon in this case, now we would move our formal charge there. And that puts that closer to, and this is an example of like, don't move too many things at once, right? Don't get overzealous. I definitely did that a lot. And I obviously just did that a minute ago. It can be really easy to be like, oh, okay, I'm going to move this here, move that here, move this. And like, yeah, if you're like up a little bit further in your classes and you're just trying to figure out like where something's going to bond to, like doing reactions, and sure. But in this case, she literally wants to see all of the resonance structures. So just move one radical or one radical, right? You have to move 2 electrons at it. Just move 2 electrons tops at a time. Just keep that like every structure, just move 2 at a time, and then you won't miss one. But sometimes for a radical, just know that you're going to see this a lot, right? Because and then you might have to move, and then so radicals, you'll have to move 3, right? Because you have to move that other one. But anyway, so, and then, we have this double bond here, we move that there, right? And so we just kind of like move that around the structure. And then in all of these, as this says, this one's sp3 hybridized, so this one's not going to participate. And as we talked about before, this one's not going to participate, even though it could, right? We could move it here, but it's just not going to, because we're going to end up with a formal charge there, and nobody wants that on a terminal carbon. So, and you can even see here, right? Like we've now turned 2 positives into 2 positives and a negative, because we had to do something with those electrons. So, and those electrons couldn't go here because it's already tied up, so that's something to think about as you're moving them around. And then if you have a negative charge, for example, we have like this, we can move. This is a good example of like how you can move your electrons around. So you want to just move your electrons towards something that's not sp3 hybridized, right? So you would move your electrons towards your double bond. That would kick these over, right? And then you would get them, so your resonance structure, oh, here it's on the side. So your resonance structure would be this with your double bonds here, and then we can move everything back, right? And so that's doing 2 jumps at once to get from here to here. But you could also, if you wanted to, just so that you can see it all, you can do it like this, and then in like maybe a different color pen or something. And then draw your electrons going this way. And then you draw your structure here to show, you know what I mean? So that way you're not like, oh, I'm doing too many jumps here. It gets confusing to get back to the side. So you can always kind of set it up in this linear fashion as well, if that makes sense. But yeah, I would say formal positive charge is a great place to start. And then after that, you'd be looking to move your non-bonded electron pair, in this case, right, to towards a double bond somewhere, or towards a triple bond somewhere, so that you can start to shift electrons around. But I would identify your sp3 hybridized atoms first, because that will give away quite a bit of information about where you can move towards. So
yeah, that makes sense. What is the ultimate goal when you're drawing the resonance structures?
Ultimate goal.
Does that make sense?
Yeah, like, for right now, your ultimate goal is like learning what like the structures look like on an energetic level, because you have to think about this as far as like these atoms and and molecules and electrons and all this stuff going on. Like, it's literally not lines, right? It's these energy density clouds that either overlap or and then these electrons, they just kind of want to like bebop around, right? And so they kind of like skip around. Like an electron might be here, and then the next second it might be here, and then the next second it might be here. And so they're just kind of, it becomes more of like a mathematical pattern of things that creates, we're getting really deep here, right? But it kind of just creates, right, anything that we know about in our, you know, reality, right? And so the idea of resonance is to be able to see, especially as you get further along, like for example, in our cyclical rings, like eventually it'll get to the point where you'll just be able to draw it like that, because we know that I'm sorry, in an aromatic benzene ring, just to clarify, right? Because we know that there's resonance. Like this is gonna go here, this is gonna go here, this is gonna go here, and now we've got a ring that looks like this. But you know, who's not lazy? Right? So like, you know, there is shorthand, you guys just aren't there yet. But so the ultimate idea is to be able to, resonance will show you where things will interact with other things. So once you get to like, say maybe like biochemistry, or you start to like move up in the levels, or even in organic chemistry, if you had to go a little bit deeper, right, you'll be able to see that like, okay, I have a partial charge here, like in this example right here that I drew out. I have a partial positive charge here, and I have like, say, an oxygen on the end of whatever, you know, they denote it like that, whatever this molecule is, there's going to be some sort of interaction going on here, right? Or like, you know, so it's really, it's building this basic knowledge so that you can like build on that and either create, because we're moving towards synthesis, you guys will be synthesizing molecules, breaking things apart, putting them back together, all of those things. And so you want to be able to understand, because when you're doing synthesis, you might get this structure, but the only way that something will react is in this structure for whatever reason, right? So this is a kind of a bad example, but I'm just trying to like give you an idea of like, you know, like, okay, it's like, say you have a bulky base, and a bulky base is not necessarily going to interact that well here, because you have this arm, this ethyl that's like moving around and taking up space, but a bulky base will interact great over here because there's nothing blocking it, right? So that's what this idea of resonance. So this resonance will build, you'll continue to build on these concepts. That's why I said like bond association, energy, your reaction coordinate graphs, resonance, these things will not go away, especially if you're going to OChem 2. So that's kind of the basis of where we're getting to this, but we're just working on like the really like simple knowledge of like how to create a structure. So that way, eventually you'll be able to say like, oh, you'll see this and you'll be like, oh yeah, I know there's also going to be a formal charge here. So, and that'll be the most likely area. Does that make sense?
Yeah, that's cool.
Yeah, it's a long game goal, you know? Any more question on resonance before we move on to our chair confirmations?
Yes, actually.
Yeah.
Looking at number 2 on the review.
Yes. Let me pull it up. What's your question about it? Let me see.
For B, she labeled it as secondary and primary. Can you go over those labels?
Yeah. 1 second. Let's see. So week 2 extra credit assignment. Let's see. Excuse me. 2B. Okay, so to confirm the structure. Is this the structure?
Say that again. Oh, sorry.
No, that's okay. Is that the structure?
Yes, it is.
2B. Yes, okay, perfect. I just wanted to make sure before I move on that I'm looking at. Okay, so provide all resonant contributors for the molecules below. Include the original structure provided. That's the only thing about resonance. Ugh, you gotta draw so many structures.
So much drawing.
I know. It's such a pain in the butt. Let's see, for each molecule, draw the actual resonance hybrid structure indicating the atoms that carry the partial charges using the delta symbol. You do not need to provide numerical values of the partial charges. Yeah, so that's an example of how so there was somebody else asking me about that. that's an example of how she will ask it in the exams of like, if you have to include the numerical, it'll literally say include the numerical value. So however many say you have across your resonance, you have 3, then each one would be 1/3, right? Whoops, not that positive, sorry. 1/3.
So like you made 3 jumps.
Yeah, no, say like your structure. Yes, yeah, jumps. I guess you could say that. Yeah.
Okay.
So say across your resonance structure, let's just say, for example, I haven't done this out yet, obviously, but let's just say that this positive charge moves here and moves here. It's not going to move there on that terminal carbon, obviously, but I'm just saying.
Right.
So when, yeah, exactly. So when we would draw the structure like this.
Right.
And then we would say that each of these, whoops, had a positive 1/3 delta.
Okay, that's
Positive.
really simple.
1/3 delta. Yeah. So, but you would only really see that once you drew your resonance hybrid structure, which is all this in green that I did. Okay. So let me just erase this stuff. So now what was your question about this?
So and it might have been when it was during her review, somebody had asked, how do you know what is the major, the minor? And in that particular example, she labeled our first one secondary, our second one secondary, and our third one primary. And then she said the 2 secondaries would be better contributors. And where do you get the secondary and the primary label from?
She might be talking about, okay, so let's do it all out together. So, and I forget who asked.
Just if it helps, what she was doing was she was just like counting the number of non-carbon like bonds, like atoms that bonded to the one we were looking at. So like the bond was carbon, right? And then she like looked around the carbon and like there were 2 bonds connecting that were carbon-carbon bonds, and she counted all of the ones that weren't bonded to hydrogen. So you can either get primary, secondary, tertiary. It's like
that's what I was gonna ask.
Yeah, it's what we did the last unit.
Yeah.
Oh my God.
No, it's okay. That's why like these things are like, you'll get them over and over again and they'll keep coming back, right? Like it's all good. So like, for example, this would be a secondary versus this one would be a tertiary, right? Because it has 3
bonds.
3 R groups, non-hydrogen. R just means an R group, just means carbon, like like some sort of carbon XYZ or some sort of like non-hydrogen.
Okay.
Right. So R group is just anything that's like non-hydrogen. So it might be, you know, like an alcohol is an R group, right? But it's obviously an oxygen, right? But it's going to be like your carbon attached to a carbon or an you know, a nitrogen. You're not going to get a nitrogen and an oxygen, but you know, whatever it is, like your amides, right? Like NC, NCOH, right? Like, so and then if this is an H, and say this is carbon, whatever, CH3, just something, whatever, just to make something up, right? So this would be a 2nd degree because it's attached to a carbon here and a carbon here and a hydrogen here. So this one doesn't count. This
counts, so it's 2.
Yeah, so this would be a 2nd degree.
Okay.
So yeah.
Thank you,
Does that answer
Jackie.
your question about this one? Yeah. That's what it sounded like to me. Okay, cool. Yeah, that's what it sounded like to me. It's like it just sounded like she was counting R group. Substituents is what it's called.
Yeah.
Cool. Substituents. Substituents is anything that's like, again, not, that's why I was saying last time, like, just think of hydrogen as like your cheerleader or your like emotional support Pomeranian or like, you know, it's kind of just like, it's a placeholder. Yeah. It helps stabilize the structure, but it really has like no, and like, it helps to either move electrons around or move charges around, but it really doesn't have anything like any like sustenance to it itself. It has a lot of purpose, but it doesn't really do anything, if that makes sense. That sounds totally asinine.
No, it does.
Yeah. Okay, cool. Okay, anything else on resonance? We'll move towards
yeah, so for the Newman stuff, Would you mind pulling, okay, is that the gap notes?
Yes.
Okay,
It's,
great.
I
Oh.
just pulled sections of the gap notes out that I thought were important. So,
Okay, because I like annotated my gap notes and put in like questions that I had for you. Is it possible to like run through those? Because like
yeah.
I have like problems with Newman projections and they continue throughout this entire unit. So like
Yeah.
I really want to like make sure we can get to them.
Yeah, let me see. Let me pull up the gap notes so that I can follow along with you. Yeah, because
Thank you.
I only just like I just went through the gap notes and pulled the material that I thought was important. Not that it's not all important, but it just, it just like is repetitive, which is good, but let me see.
Do you think with the Newman and with the Sawhorse, the best thing to do is have your models made?
Yeah, that's what I would do.
Yeah.
Honestly, I really enjoyed this part of class and it was very intuitive for me. So I could like imagine myself spatially moving these things around without them, but like I never used them, but I still did bring them with me to the exam. So it's just when in doubt, get your models,
Okay. Mhm.
Okay, so this is going to be part of the alkanes complete notes, correct? Not the resonance, obviously.
Yeah, so if you don't mind starting from pretty
What
much the
page?
beginning, the section lesson 2 conformations of alkanes.
Lesson 2.
So you're almost there. You just
Like
up
it's
there.
page 4. It says conformations of alkanes on it.
Page 8.
It's the page
Page
right
5.
before.
Page 4. There we go. Got it. Yep. It's the page right before page 5. No. Um, okay. Yeah. So yes, we are there, and this is actually where I pulled this from. But
Yeah.
okay. Yep.
So starting right there, it would be really helpful for me if you could like color code which hydrogens are which. I want to make sure I'm understanding how to get the proper orientation.
Mm-hmm. Yeah. So you have to pick you have to pick what's going to work for you, and you have to be consistent with that method. So I will give you one way to do it, and you can flip it, but you just have to make a commitment to whatever way you decide. So in this example, we are looking, as we can see, this eye. She's always so good at drawing the eyes in the photo.
Oh my gosh, I know.
And I was like,
Mine never look like that.
yeah, mine always look like anyway. But yeah, okay. So we have this eye, and it's looking at this carbon here. And we're looking straight down this way. Okay.
Yep.
So, and we remember, hopefully, we remember that anything with a line is in the plane, right?
Right.
And anything with a wedge is coming out of the plane. And pick another color
Isn't it
here.
going up?
Anything, it's coming out of the page. Out of the page. A wedge is coming out of the page, and a dash is going into the page.
So which lines on the Newman represent coming towards us in a way?
Yeah. So this is what I say, pick your poison and stick with it, right? So in this case, imagine that this Newman projection, right? So when I say like pick your poison, whatever way you're looking, you have to make sure that you know like the direction that you're looking at. So this carbon here, let me see. This carbon here, I'm going to circle in pink. And this carbon here, I'm going to circle in blue. So this carbon here is this carbon here. Okay. And I know you know this stuff. I'm being super simple, step by step, explicitly explaining this, right? And this blue carbon here is the carbon that's hidden behind this, right? And I'm assuming that you know that when we putting this circle here helps you to determine this plane versus this plane, right?
Yeah, I do know that.
Perfect. Okay. I just want to make sure. I just want to be super explicit. I don't want to miss any details. So if you are looking at this pink carbon that we just labeled, and you're looking at it in this direction, okay? So what I used to do is I would, you know, when I was explaining it to my friends, right, that I was in class with, is I would literally hold the paper up. Now imagine that you turn your body so that your shoulder is moving towards your paper. Your right shoulder, in this case, is moving towards your paper. Don't move your paper, but just move your right shoulder towards your paper and look in the same direction that that eyeball is looking. So your left shoulder will be away from your paper and your right shoulder will be towards your paper, okay? So now on the left, on your left side, if you were in line with your page, the left side would be anything that's coming out of the paper, right? So sometimes it helps to, that's why they say make the models, right? But if you don't have your models or whatever, you're trying to do your homework, is like you can literally just, if I'm looking from the right, if I'm looking from the right to the left, that means that I'm going to dip my right shoulder, say you're at your computer, dip your right shoulder towards your computer and pull your left shoulder away from your computer so that your left shoulder is now where what would have been behind you, right? And so now you're looking in the same direction. So now imagine that you're in the plane with your paper. Anything that's coming out of the plane, the wedges, are going to be moving to the left. And anything that's coming into the plane, which is the dashes, that will be moving to your right. So that's how you will decide, in this case, our H here at the bottom is straight up and down because it is in the plane of our site. And then our wedge, and this is obviously hard to tell because we have all H's right now, but our wedge is going to be on the left of our plane because we have turned to look at it and the wedge is coming out of the paper and our left shoulder is moving in that same direction, right?
Yeah.
And so now you have determined that if you are looking from the right to the left, your wedge is going to be on the left side of your page.
Okay,
So,
yeah, that makes sense to me, that one.
Perfect. Okay.
Okay, thank you for going through all of that.
Yes.
So if we can just
Yes.
like, you know, try to run through like,
Yes.
you know, a good number of them.
Yes.
The
Yes.
one, so now go to the one directly underneath, like literally right underneath the one we just did with like the two orbitals and the, like the two lone pair. Yeah, that one.
This one?
Yeah.
Yep.
So then, in this case, the orbitals that have like the two electrons in them, where are they? Are they still in the plane of the paper? I just want to make sure.
Yep. They are in the plane of the paper because as we can see in this, right, carbon has 4 bonds. And we can see that this is coming out. This is coming out. I'm not keeping my colors consistent. I'm so sorry. This is going in. This is going in, which only leaves in the plane left. And so these carbons, sorry, these carbons are in the plane. So that means that these guys also have to be in the plane. And so, yeah, go on.
Sorry. And how do you know for this example, like, what's the giveaway that this is going to be eclipsed?
Because they're both in, like, these two are both in the plane like this.
They're
So
behind.
Yeah, so see here.
Looking at C1, C2.
Yeah, so
I see it.
Yeah. So if you have something like this,
The models are really helping me, Jackie, if you have them.
Okay, thank you.
let me see like this. I want to make sure I draw it correctly. You're supposed to draw them the same. So anyway, if you have it like this, then you know that your in planes are going to be eclipsed because they're running along this, they're in the same line with each other, so to speak, versus, and so are these, right? Versus these ones we have, as we saw in this pink highlighter up here, they're in, they're 180 degrees from each other, right? So
Yes,
they're top
I
and bottom.
see it now.
Yeah. Yeah.
Okay. Okay, and then if you can go to the next page,
Yeah.
where we're talking about butane, the butane example.
Mhm.
I just want to confirm with you that you just look at the like CC single bond on the bottom, like because these structures get more complicated as we go.
Yes.
So I just want to make
Yes.
sure, like, what is the defining characteristic of your starting point? In this
Mhm.
example, the CC bond.
So let me see if they have, let's see, two unfavorable interactions. So this one is literally telling you where to, and she will tell you from carbons 3 to 4, or from, I'm sure you've seen that, right? Like, I'm pretty sure
Right.
that's in her extra credit, right? And so in this case, there's only 4 carbons. So she'll say from carbon 2 to 3, right? And so like, there's only one way to do this. And this is a symmetrical molecule, but she's literally has written out, right? They've written out that you're looking from this carbon here to this carbon here. So what you start doing is you will, like you see here, you have your CH3s. You're not going to do, as they get more and more complex, right? Say you have, CH2, sorry. CH2, CH3, let's just say, and then, you've got a hydrogen and whatever. Anyway, what you end up doing is you end up literally just writing out, pro, methyl, ethyl, H. I didn't do that right. Sorry. Let me see. Let's just say this, right? And let's do this. Jeez Louise. You guys know what I'm trying to say, right? And then we've got this, and then we've got, right? So like you'll end up literally just writing ethyl, methyl, phenol, say you whatever. So this is a phenyl group, like whatever it is. This is what you'll end up writing. You're not going to end up writing like a structure like this because all this is just like a long chain. It's just like a big, bulky something, right? Like you'll see a lot of T-butes, right? Because all that is just it's a bulky, 4 carbon, whatever, right?
Yeah.
So,
Yeah.
So this is what you'll do, and then you'll literally just have your, and maybe you'll want to draw lashes if you're feeling froggy, right? No, as long as you draw. Then you draw like where are you looking from, right? And where are you going? So
Yeah.
yeah. I don't
And
know if that
then
answered your question. Sorry.
yeah, I know. I mean, it is all very helpful. I just have quite a few, so
Yeah, no, please.
thank you.
Yeah.
It's really helpful.
Yeah, no
If
problem.
you could go to the next page, now page 6.
Yep.
And at the top of that page, you know how there's
The
like the
diagram.
4. Yeah.
Yep.
I have a question regarding gauche.
Yeah.
I just want to confirm this only occurs when these two like substituents, if you will, are exactly 60 degrees apart. Is that correct?
Yeah, so and you can see, right? So you can see in this diagram, I don't have it up here, but you can see in the diagram it says for anybody listening to the recording, page 6, top of page 6, 0, 60, 120, 180, right? And so in this example, these are the lowest possible energies and like the high, right? So 0 degrees is everything is eclipsed, right? And it says total eclipse because you have the 2 biggest group, which are methyls, you have those eclipsed with one another, right? So that's why that's considered a total eclipse.
Yeah.
Whereas the next one, you've now rotated it And so now you've got these two that are next to each other. So as far like, you're not gonna get like, oh, this one's 46.5 degrees and this one is 62.7 degrees. You know, what's the percentage of the gauche energy that you're not gonna deal with that. Like,
Yeah.
it's gonna be like if they're next to each other or they're eclipsed.
Yeah, and no, and I appreciate that. I just more maybe just didn't understand fully from the lecture what the gauche was, because and we'll get to this like at the
Yeah.
end, but in the last page of this unit, you know, the professor made a comment to the effect of oh, in this case there actually is gauche even though these two substituents are equatorial, and I think there's something I missed
Yeah.
regarding what participates in a gauche. So can you just clarify that for me?
Yeah,
'Cause
sure. So
it's-
gauche is like when your substituents are close to each other, but they're not eclipsed. So remember that we have these like, you know, and this is a great way to kind of look at it, is like we have these energies. So as we see, oh my gosh, I'm so funny. I'm like scrolling on my computer thinking you guys are seeing this, but I forgot you're on my iPad. So as we see here, right, there's these you know, the atoms that are right now, or well, this is like electrons, right? But you know, they're very close to one another and they don't want to be, they want to like repel as much as possible. So as we shift things around and move things around, we notice that there's like more overlap than others. And the bigger your substituents get, the more they want to be away from each other. Otherwise, there's what's called strain energy.
yeah.
And so gauche is when you're gonna experience gauche when you have substituents next to each other, versus and there is something further along here. Let me see, because I know it can get a little confusing. Let me see. Oh, here we go. Oh, I didn't put it on here. Oh, this is it. Yeah, go ahead. Yeah.
Yeah, there's just something about needing like the substituents to be axial rather than equatorial. And that's
Yeah.
the part that I didn't catch.
Yeah, so that's when you're doing like chair conformations, right? Yeah. So that's when you're getting down in this region. So now we're talking about, so, and maybe this, you can kind of see how we have some gauche interaction here. So it's when you have these interactions, like, so there's some stuff that's like what they call like unavoidable, right? And so like, and they have you, I think, add it as like just a ME, whoops. Where is it? I know I have it on here somewhere. Oh, I think this is it. Oh, here's an example of where we're talking about axial versus equatorial. So yeah, so here, even though these guys are equatorial, there's this gauche interaction. Is that what you're talking about?
Yeah, it is, and if let me just scroll real quick to the last.
Yeah, please.
Yeah, what I'm specifically referring to is literally on the last page of this module, page 14, the last part. The professor made a comment that the methane and ethane, I think that might be the one you're looking at. Yeah, yeah, that's the same one. The methane and ethane have gauche interaction, and then she said, even though they're equatorial. So that made me think that in most cases, equatorial don't have gauche because she like qualified it in that way.
Yeah, they don't typically because they're far away from each other, but because they're on neighboring carbons, you would still have some gauche interaction. Like, for example, if you know, it's hard because no matter what, you have something, right? But like this and this are not going to have, they're even not even on the same, one's axial, one's equatorial, but let's just say that let's switch these two here, right? Let's switch the methyl and the hydrogen. So let's just say for this conversation that we're gonna put the hydrogen here and we're gonna put the methyl here, right? Just so that we can see that these are both equatorial. You are not gonna have gauche interaction because they're so far away from each other, right? Like this is, there's a carbon between them. But these two, even though they're both equatorial, they're only one carbon away, right? So you're still gonna, and you're talking about methyl, and you're talking about an ethyl, which are single bonded, right? And we've got H.
Even though there's a hydrogen in between?
No, there's no hydrogen in between. This is off of this carbon, right? So let me draw it down here. So what you have is, let me make sure I'm drawing this correctly. Oh, there it is right there. So what you have is, let's just ignore the hydrogen that are on the, we're going to ignore these hydrogens here that are part of the group, part of the benzene ring, but we're going to just draw, right? I'm just going to draw a dot for a carbon, right? And then we have 2 hydrogens here, and we have 3 hydrogens here. And then we have this, right? And these are part of their benzene ring, right? So these don't move, right? That part of your benzene ring doesn't move. But then you have this here, right? And remember that all of these, not only can your chair kind of move conformations a little bit, but all of these bonds have full rotation, right? So these are going to be swinging around too. And so this diagram here is it's just showing you, it's ignoring the hydrogens, but it's showing you this piece here. And all I did was just draw out the methyl and the ethyl. And then I ignored, just for this conversation, I ignored these two. But you know, if you wanted to also add those on, because really like they would be having their own interactions because they would be like repelling groups, right? Is that you have a hydrogen here, and then you have a hydrogen here, which don't tell Dr. Pillai, because this obviously, this looks like it's, and really it should be. Oh, don't tell the organic chemistry police. No, not her, but let me see. Okay. So then we would have this one here, and then this one here, and then this would have 2 hydrogens. This would have 3 hydrogens, right? I just wanted to make it obvious that this was not equatorial. And so that's what we're seeing here. So we're seeing these hydrogens kind of floating around, and we're seeing these bonds spin around, right? And so that's why you're gonna see that gauche interaction, because even though they are equatorial, these can again move in all directions, right? And so this has this spin effect. Does that make sense?
Yeah, and no, it does. And I really appreciate you going through all of this. Is it possible to go back to page 6 though?
Yeah.
I feel after you explained the wedge and dashes, I feel a lot more comfortable with that. And now
Cool.
on page 6, we get to the line, angle drawings where there are no specified wedges and dashes.
Yeah.
My question is, we know based on looking at this, drawing and the octet rule that we are going to have hydrogens that are added in. And depending on how we draw our hydrogens, we can draw it, upwards or downwards. And so my question is like, how do we translate the line angle drawing to the Newman and get the orientation correct and be confident on it?
Yeah, okay. And I think, and I believe this is what's here is the example problem at the bottom of page 6, correct?
Yeah, that's the one.
Yeah, okay. So, and I think this is the one where I was talking about where you just need to like pick one. So the left-hand one is tilted a little to the right. The one in the middle is tilted a little to the left. So that is the atoms. You can get behind to the far
Yeah,
right.
that third one,
For a second.
they're trying to make the point that it's not reasonable, and I don't understand. I'm missing the point that they're making there because I don't understand why.
The third one, this third one, or this third one?
No, the one that has the line through it.
Oh,
The
this one right
bottom,
here.
yes.
Okay. Let me just read it. Let me get to these. Okay, so it says that, so this or rotate a little, not, but it's saying not. What's the differences? Ethyl. Oh,
Hydrogens in the top left are different.
yeah, so what this is telling you how to draw it correctly. It doesn't want you to draw it like this. It wants you to draw it like this. So whatever side you have to, that's why I was saying before, you have to stay consistent. See how, so like if your wedges are on the left and your dashes are on the right, then it has to be like that for top and bottom. So in this example here,
But
they
I don't
have,
know how to even get the wedges and dashes from the Newman. Like
yeah, you
that's
do.
what
Yeah, you do. I'll tell you how you know. Because we just went through it. But now we're doing it here. Now we're just doing it backwards. Now we're just doing it backwards. So if we're looking at this like this, remember that anything on your left is going to be your wedges and anything on your right is going to be your dashes. So, or in this case, right? Like that's why I said you just need to pick something and stick with it. So in this case, it's asking you, no, sorry, look at the relevant method. So in this case, it's saying that we can look at this and say, hey, we have a hydrogen and a methyl on one side, and we have a hydrogen and a hydrogen on the other. Okay, well, in this structure, in this first one, right, we have a, I'm gonna do a different color, hydrogen and hydrogen here. Yep.
I thought the wedges were coming towards us.
Yes.
So I thought that meant they're on the left.
Well, it depends on where you're looking at the structure from. So this way, oh, sorry, I did this backwards. Sorry. Erase what I just said, okay? Work with me for a second, sorry. Oops, okay. So we're looking at this structure now. We're just gonna do it backwards, right? So we're looking at the structure now where this carbon here, so if we're looking from the left to the right, this carbon in yellow, which means all of these structures in yellow, whoops, all of these structures in yellow are a part of the carbon that's now on your left, right? So now we're just doing this kind of like backwards. So now instead of looking, yeah, oh, it says it right here, right above us, right? So instead of looking at it from this carbon, where this carbon would be in front and this carbon would be behind, now we're taking it and we're using this 3D structure where imagine that there is a carbon behind it, right? So there's a carbon here that has an ethyl and a methyl and a hydrogen coming off of it. And we're looking at the bond right here so that this carbon is to our right and this carbon is to our left. Okay, so in the same way, let's do it the exact same way that we did before. Okay, so because we're working on a 2D plane, and so it does make it really a challenge. So you're not the only one, don't worry. So now if we're looking at this and we remember that anything that we can see lines for here within this circle is a part of carbon whatever. Let's name it carbon A, right? Just, or carbon 1, right? Let's just call it this for now, right? Carbon 1, which means that anything that's behind it that we can't see the lines for all the way through is for carbon number 2, right? And now we're looking from the right to the left. Okay, so we're going to do the same exact thing that we did before. We're going to turn our right shoulder in towards the page or in towards the computer. And imagine now that everything that's in front is now to our left. All of those yellow substituents, the carbon, the yellow substituents, those are all on our left side because we've now physically moved ourselves to the right of the structure, right? But we're looking to the left. So your front carbons in this 2D structure are now going to be on your left. So now we know that anything on this side, anything that's closest to the eyeball is going to be a wedge. This is always going to be your plane, and anything that's away from the eyeball is going to be your dashes. Is this starting to make sense a little bit here? So now,
Yeah, I follow you everything except just the last piece of literally the last line. Can you just repeat everything
yep,
away from you is what?
yep. So if our eyeball is on the right side of the structure, which means that we are looking towards the left of the structure. So any substituent that is, so let's start with the line. Let's start with the center, right? This is your plane. That's your plane right here.
Yeah.
The ethyl and the methyl, that's your plane. We are looking this way. So that means anything that's closer to the eye than the plane is going to be a wedge. It's going to be coming out of the plane. Imagine that this is a piece of paper now, right?
Yeah.
And anything that is on the other side of the plane from the eye, those are going to be your dashes.
I see. Okay.
Does that make sense?
Yeah, that makes sense.
Good. So as we see, they've drawn this plane right here, right? So that's the plane that's in line with this eyeball. That's, in between this one and that one back there, right? So now we see that anything, and this is where multiple colored pens are great, because because you can mark up your structure to make sure that things are lining up correctly, right? So now let's go back to our yellow is now going to be, so anything that's in front. So if you're on the right, if your eyeball is on the right, anything that's on that top carbon is going to be on the left side of the structure. If the eyeball is on the right of your Newman projection, anything coming off of your off that first carbon, that top of the carbon, is now going to be on the left side of your 3D sawhorse.
Mhm.
Okay. So now we want to see, like, okay, so now we have a hydrogen, we have a methyl that should be in the plane and on the left side. We have a methyl. Ugh. We have a methyl that's in the plane and on the right side. Now we have one hydrogen that is coming out of the plane on the left side. One hydrogen that's coming out of the plane on the left side. One hydrogen that's going into the plane on the left side, right? And they're both still on top. See how both these hydrogens are on top and the methyl's on the bottom? You want your sawhorse, I keep wanting to say seahorse. You want your sawhorse to line up with that, right?
Yeah.
So now same thing. So now we're going to work on the back carbon, which will now be on our right side. So the back carbon, if you're looking from the right, will be on the right side of your structure. So now we have a hydrogen that is going to be a wedge on the bottom. There's a hydrogen that's going to be a wedge on the bottom. We have an ethyl that's going to be in the plane on top. Ethyl in the plane on top. And then a methyl dashed on the bottom.
Yeah, I see it. That was great. That was
Awesome.
yeah.
Cool.
Okay, so then now they're saying, okay, just rotate it a little bit. And I see how they got from to number 2.
Mm-hmm.
And then what is wrong with number 3? Because I don't even see the difference.
Mm-hmm. Yeah, so that's what I was saying before. See how you have, this is where you kind of have to pick your poison. Your wedge, you have your wedge on the left, wedge on the left. Or sorry, dash on the left, dash on the left. Wedge on the right, wedge on the right. In this, so we have dash left, wedge right. Dash left, wedge right. In this one, they have wedge left, dash right. Dash left, wedge right. So whatever you choose, keep it consistent. If your dashes are on the left, your dashes need to stay on the left. If your wedges are on the right, your wedges need to stay on the right. Once you do a new structure, then you can do a new structure, right?
Yeah, I
But
see.
you have wedge and wedge versus, dash and dash, right? So they're not consistent.
Yeah, no,
Okay,
that was.
I was just wondering
Thank you.
how that was going.
Oh, I just muted her. Okay. Yeah.
And then for the one right above, when you're just given the line angle structure,
Yeah.
and you don't have like
This
any
one?
guidance based on like what's a wedge or what's a dash,
Mm-hmm.
how do you know, yeah, basically the orientation of the Newman projection?
Yeah. Yeah. So you're always, so you're gonna have to pick. So I want to say, and before I say too much, I want to make sure that, let me see, in the next example, ethyl, yep, and then methyl on the bottom. Yeah. So your largest groups are anti. I'm just trying to see, I want to make sure that I explain this correctly and I'm not saying something messed up. Because I want to say that this is where it's kind of like you want to choose. So, okay. Yeah. So this, did I add it? I think I did. Let me see. No, I didn't. So it's going to ask you, I just want to make sure I didn't add it. Yeah, so in this example, it's be the top of 7. It's gonna, so this is saying like from the IUPAC name, draw out the structure, right? And then pick something. So it's going to ask you the question, if you have something like this, it's going to say, choose the highest energy and choose the lowest energy conformations, right? Or it'll say, choose the, it might even say like, choose the highest energy Gauche or lowest energy Gauche or highest energy eclipsing or lowest energy eclipse, right? So it'll say something like that. Now, in that example, you'll see that the isoprope is on top and an ethyl is on the bottom because everything wants to be low energy, right? So your biggest groups are always going to be opposite. And it says that on there, largest groups are anti, right?
And I
But,
totally understand that point. Yeah.
Yep.
I just don't know how they get to the Newman projection from the original line angle.
Yeah, because there's 3 methyls, right? There's a hydrogen and 3 methyls. So in this case, right, the carbon on the right, the one that's closest to the eyeball, there's 2 methyls. So there is no like one has to be wedge and one has to be dash. There's no other option, right? And then for the carbon on the left, on the bottom, there's a methyl and a hydrogen. Well, because there's 2 methyls on top, it doesn't actually matter because again, the question will ask you what is the highest energy conformation, or what is the lowest energy conformation, right? So it's going to literally ask you that. Now, say that there was a hydrogen and a methyl on both the top and the bottom. Like we're not talking about the isopropyl or the ethanol. We're just talking about those other 2 substituents on those carbons. Say it was, they both had a methyl and a hydrogen. Well, if the question asked you for the lowest energy conformation, then you would put a methyl as a wedge on one and a methyl as a dash on the other, right? But because there's no option, there's only one option for this one. There's no other way to situate those due to the fact that like your largest groups are always going to be anti to one another. Does that make sense?
Yeah, no, that really does. I think I see it now in terms of it's kind of process of elimination a little bit for some of the structures. In the sense that the one you just explained, because there were 2 methyls pointing up, then you know that the other conformation has to have your methyl and hydrogen pointing down. That's my question. I was like, how did you know that the hydrogen was pointing down and not up? But it can't be up because there's nowhere
because your
else for it
probe's
to
on
go.
top. Yeah, exactly. So in this case, like you can see that like your isopropyl's already up and your ethyl's already down. So your lines, you're in the plane, pieces of the molecule will always be your largest ones. And then after that, whatever's left over is left over, right? So in this case, ethyl and isopropyl are the biggest ones. So isopropyl will go on top, ethyl will go on bottom. You could do it vice versa, right? But then you would swap the whole thing around, right? Then your two methyls would be on bottom instead of on top, right? But in this case, the way the structure is drawn, isoprop's up on the upper left corner and ethyl's on the lower right corner. So those are your planes. So then you can only, so then these smaller groups, these four smaller groups, two methyls on top on the right and a hydrogen and methyl on the bottom on the left, those will go in their respective areas. So the ones on the left will go down because we've already made that decision, that distinction that the isopropyl on that carbon is in the straight up position. So there's nowhere else for it to go.
Yeah, understood.
Cool. Cool. All right, what else?
I had another question on number 9 on the review.
Yeah. Yep, let me pull that back up. And Jackie, feel free to keep, get your questions prepared. I'm here. Okay, so number 9 on the review. Perfect. This is another Newman 3D sawhorse projection situation.
Yes. So when she is coming up with the calculations to see what's the lowest energy and the highest energy, in the staggered conformation, how do you know what is interacting with each other?
Whatever's next to each other.
But no hydrogens.
Hydrogens, no. It's only like you'll see in this like if you're looking at 9 and you'll be given this chart. Hopefully if she hasn't changed that, but here's a portion of the chart right here on the screen that I have pulled up, right? But you'll see, so like in this gosh interaction, so what gosh means is that you have two that are next to each other versus the eclipsing is when, just consider that we draw it slightly to the side to show that there is another one there, because otherwise it wouldn't look like anything, right? It would just be this and then this. So, or whatever. That wasn't even a good example. It would be like this and this, right? But yeah, exactly. Yeah. So, so when we have the gosh, it's just anything that's next to each other. Now say, because yes, obviously you draw hydrogens, but let's just say that this, I don't know why it's doing that. Say that this is your thing, right? But you have like hydrogen, ethyl, let's put a methyl here, hydrogen, methyl hydrogen, right? Like the only gosh interaction that you have is right here.
So the particular one I'm looking at, and I don't, you guys, or you don't have it drawn the same way that we do have it on the review, I'm assuming, is she's got, excuse me, 4 methyls next to each other.
Yep.
So
I have the review up too, so I can look at it.
Okay.
Yep, I have it up. Yep. So you have, so this is your structure. Right?
Okay.
That's what you're talking about?
No. Oh wait, maybe.
If I'm looking at the right one, review 2, yeah, number 9.
Yeah. Oh wait, number 9. Yes. Maybe I'm looking at it wrong. Hold on.
No, you're fine.
So I'm looking at it as the not the sawhorse. Like she had us draw both.
Yeah, she has you draw both the sawhorse and the Newman, but this is this is the structure that I'm seeing on here. Let me just read it. So from 2, 2, 3. So for the structure shown below, yeah, so this is the structure. She has it drawn like this if we want it to be, and correct me if I'm wrong, right? But she has it drawn
I'm a dummy. I'm sorry. It's 10. That's why we're confused here.
Oh my goodness. Okay. Oh, this is energy difference.
I
So
was
draw
like,
the
what is
indicated.
happening?
Yeah, no, you're fine, you're fine. Don't worry about it. Okay, so let me see. So this one says, for the following structure, draw and indicate the low and high energy chair conformations and calculate the energy difference between the two conformations using the table provided. So this is where you have to draw your chairs, right? So you got to get really good at drawing chairs, and it took me forever to figure out how to do them, and mine like aren't pretty, right? But whatever, they make the point.
Draw a bad bow tie.
Yeah, exactly, right? So like I could do these over and over again and fuck them up every time. So
yeah, they still look different every time.
Yeah, exactly. Okay, so now let me just, it's really good to just have a method and stick to it, whatever it is, right? So I'm drawing out the so this is your original structure.
Yeah. Mm.
Okay, cool. That's your original structure. So how
So you don't have to draw so much. The one that I'm confused about is not the sawhorse, but the Newman, drawing the Newman. And that was kind of how she showed us how to count the interactions, because you could see them really well next to each other. And she had 3 interactions for the second one, but 2 of those methyls are being used in all 3. All 3 interactions? Does that make sense? Is that allowed?
2 of the methyls? Oh, are you talking about methyl gosh interaction? Like you're adding that in every time? Is that what you're talking about?
Hold on. Can I take a picture and add it into here? Is that allowed? How does that work?
Yes, let me see. Let me stop sharing and you do a screen share. Let me know.
I don't know how to do that.
So at the on the thing at the bottom, it should say share screen, but let me know if it doesn't let you, and then I have to.
No.
Does it say it doesn't allow it? Hang on one second.
Yeah, hold on. I'm just
Advanced
gonna
share.
see if I can.
Oh no, it says all participants. No, you should be able to. Unless you're on your like phone or something, then it might.
No, I'm on the computer.
Yeah, the thing at the bottom where it says like new video security participants, there should be one that says share screen. Next to like reactions.
Oh, now it worked. Let's try that. Oh my God. Of course, I have like my settings set all weird. If Jackie, if you have a question while I'm trying to get this to work, pop on.
Yes, I always have a question. Don't worry about that.
No worries.
Page 8 now.
Okay.
This might be a quick one, but
Okay.
for the first diagram that they show, that is the cyclopropane.
Yeah. Am I on the right page? 8. Yeah, the very top, before the right above 2.3 cyclic alkane, or
oh no, yeah, where cyclic alkane is.
oh,
yeah.
okay, there we go. Oh, cyclopropane. I see it now. Yeah. Okay, yeah.
Yeah, so in this Newman projection, the CH2 group has that like diagonal line, if you will, basically because the front and the back carbon sees it. I just want to know, when I built the model, so when I'm looking at the model and you're like looking from the vantage point of the eye, you can easily see what the front carbon sees, right? You see that it has the 2 hydrogens and then it sees the CH2 group. How do you flip your model so that you're figure out what the back carbon sees? Do you like literally turn it around or what?
Yeah, I would just like literally turn it around. So something that I did too to help me is I would use when I made my models, if I made like I didn't make these 3 models, but I would like these 3 carbon models. But like when you would have like, you know, a front and a back, and then you'd have your 3 substituents coming off of each of those, is like I would use, because it doesn't, as long as you know, it doesn't really matter as far as like what your models look like. So I would use different colored atoms for the different like things, so that I could identify like this is the front or this is the back. So like on my like front carbon, I might have like a blue one, like for my substituents, I might have like a blue, a green, and a pink, because I would be able to identify like on my page, like, okay, this one's blue, this one's green, this one's pink, or like whatever it is, you know, instead of doing all of them the same. Does that make sense?
Mm-hmm.
So that you're able to like identify, because once you start moving stuff around and what if you make chair conformation, then you start to like flip them, and then sometimes if all of them are the same, it can be a little hard to identify like what has happened, you know.
Mm-hmm.
But if you're trying to just use your, I don't think I ever saw one like this where you would have like that 3 carbon cyclo excuse me. So I wouldn't I wouldn't, this wouldn't be a model that I would build for my exam. But they're pretty easy to build, like, you know, if you needed one last second. But yeah, just literally turn your model over, because this one's asking you to look from one carbon down the line of the other carbon at the bottom, and then that top carbon, the top CH2, is what you see on the left as like that, you know, carbon that's connected to both. So yeah, and they're all eclipsing, because they're all, each of those carbons is holding things on at 109 degrees, right? So this would be an
Yeah.
entirely eclipse. There's no movement to be able to, and that's why there's high strain energy.
Okay. All right. Thank you.
Yeah, you're welcome. You're welcome. Nicola, or was it Nicola? Was it you who? Oh, I can't figure it out, but it's okay. I think I understand now that I'm looking at it. Feel free to go back to your screen. Oh, okay. All right. If you have another question, you know, feel free, hop on, let me know. I'm gonna share my screen again. Let me see. Oh, that's fine. There we go. Okay. There we go. Okay. Okay, now what? What's next?
Oh, is it anyone or?
Whoever wants to ask questions.
Okay, just for the chair confirmation in general,
Yeah.
so you do this anytime you have a cyclohexane, right?
Yeah. So this like drawing. Is this what you're talking about?
Yeah.
See, you're not supposed to draw them straight up and down. It tells you that, and I do every
Yeah.
time.
How do you know if you draw the one that, like, you know how you can do like 2 different, you know, chairs, like they're kind of like mirror images of each other?
Yeah.
What's the difference, or how do you know which one you're supposed to draw?
Yeah. See, it takes practice, my friends. Like, this is not easy. This is not an easy skill. I spent a lot of time. You should see my notebooks. I had just have a million horrible looking chairs because it's just so, oh boy. Okay, so when you have this chair versus, hang on, let me see if I can do this. Versus this right? Like that's what you're talking about. Oh gosh, that looks horrible.
Yeah, those are the ones.
God. Dr. Pillai just makes everything look so easy. It's so annoying. Like, I can't. Okay. Yeah. So you have This is how I tried to like, okay, a short line, a long line. That's how I tried to remember it. And then I would do a short line and a long line, and then a short line and a long line. That's how I tried to remember it so that I would do them differently. Okay, they're not pretty, guys, they're not pretty. Let's just get that out the way. So, so pick, that's what I was starting to say with this. Pick something. I did the top of my carbon, the top of my cyclo in this example was the number 1, and my upper right corner was the number 1, right? Like just pick something and stick with it and never give that habit up. As long as it's consistent across the board, it does not matter. This could be your number 1, and this could be, whoops, your number 1, right? This could be your number 1. As long as you're drawing it consistently, that's all that matters. Now, when you want to know, you know, should it be like this way or this way? Well, in this example, there's a really great way. So if it's pointing up or if it's pointing down, then you're going to have the axials. Wait, if it's pointing up, sorry. There we go. Sorry. Pointing up, you'll have it like this, which means that so when you have your arrow pointing up, right, your axial is going to be pointing straight up, versus if you have it pointing down, your up is going to be on an equatorial line. Does that make sense? Hopefully somebody told you that. Okay, cool. So then when it would matter, right? And then sometimes like when you get into like all this stuff, then it's like, well, where's that? And this downward one looks like it's part of this thing, and it gets all funny, right? But anyway, here and that's there and that's there and this is here. And so when this stuff actually matters is like when you're, so I always draw it so that this carbon for me is number 1 and this carbon for me is number 1, right? So it's just going to depend on like what your drawing is. So if it's saying that your carbon number 1 needs to have like, you know, has an axial ethyl, right? Then that means that like for me, it would need to be like this, so that my ethyl was here. Versus like in this case, my up would be like this. Well, because then you shift this way, right? Then you have it down here, and then this. Oh boy. So it's just going to depend on what your question is asking you. So you'll just have to like identify that. But if this gets shifted down, then this will be my ethyl. Oops, because this is down. My ethyl will be here. Let's just say I put a hydrogen here, right? And my hydrogen's up and my ethyl's down. So it's just going to depend on like what you choose for your pattern and what your what you're drawing.
Yeah. Okay. Yeah. That makes sense. Thank you.
Yeah. No problem. I know it starts to get messy and it starts to look crazy, and I'm sorry, I'm not as neat as Dr. Pillai for sure in her videos. It makes it look so nice. Okay, what else? Don't beat yourself up over chair conformations. It will come with time, I promise. It will get easier. You know. What else? Let's see, that was page 8. I'm on 10 now.
Just for the page you're on right now, real quick, the top diagram, no, no, the ones in black, sorry.
That's okay.
So do you see like the third model, how you have the equatorial, what is that, ethyl?
Yep.
And then looking at the first Newman projection, how the ethyl is basically in northwest corner. How do you know that that equatorial ethyl is going to be? Oh, I mean, yeah, I was looking at the first and third, but the third and fourth is fine too. Yeah, how do you know that?
Oh, sorry, you were looking at this.
Yeah.
Sorry. Okay, yeah, okay.
How do you know that that ethyl is going to be there?
Okay, good question. All right, let's see. How many of the following represents? Oh, this is asking for you to look at these and decide which one. So these aren't necessarily all correct. Let me see. How many of the following?
Sure.
Sorry, what's that?
So this is kind of comparing like the nomenclature. Huh?
Yeah, exactly. So, oh, and here's the answer. I did put the answer in here. So I was like, I don't even know where I got this from. But yeah, this is a homework one. So you can see here that like there's not all of them. So this one isn't a representation. And this one, and these ones are. So you're asking, how do you know if it is or isn't? Is that what you're saying? Well, this one, if you look, yeah, you'd have to do out the nomenclature first, right? So dimethylhexane. So here's this. And then we have, so if this is 1, 2, 3, 4, we would have 2 methyls here, and then we would have an ethyl here. 1 ethyl dimethyl, yeah, 4. So in this case, if you look at this structure, we have 1, 2 carbons between each of them. And in this structure, there's only 1 carbon between each of them. Because see how the ethyl and the methyl are off of these front carbons here. So that means that there's only that 1 structure in between. Whereas this one has 2. This one has 2. This one, this is on a front carbon. This ethyl is on a front carbon. And this ethyl and these methyls, excuse me, are on back carbons, which means that there are 2 between them. Does that make sense? Here's 1 and here's 2, because the green dots represent carbons that do not have substituents on them. Does that make sense? Was it Jackie you were asking that? Oh, and here's the, I always do more work than I need to, right? But here's an example right here. This is why, right? Because this is what your structures wants to look like according to this. And this is what these projections would look like if you were to turn them into these. So hopefully that's clear. Let me see, let me make sure I have, perfect, okay. What else, so anybody else? Jackie, you got more questions? Nicola or Claire? Let's see.
Yeah, sorry, I'm just looking to see if I made any other question annotations.
Yeah, you're fine. Let me see. This is top of page 9, or sorry, middle of page 9 here. Talking about the Gauss interactions. Oh no, this is, yeah, 0 strain. Maybe I have that further down. Nope. Let me see. And then, yeah, so a lot of it's really just going to be like, where are you? These are like really great to just write out how you're looking at it. Like, for example, this right here, she's asking you to look from this. This is the front and this is the back. So, that means that, this carbon and this carbon are going to eclipse, right? And this carbon, right? So a lot of it is like, honestly, doing a lot of like color coding sometimes and just saying like, what is the structure going to look like if I were to look at it like that? Let's see what else. Yeah, and sometimes when you get structures like this, it gets like, what am I even looking at, right? Sometimes it can feel like a little difficult. So, and this is talking about those like hidden gauche interactions, right? Or we see that these methyls and ethyls are within 60 degrees of each other. So that's why we're getting that gauche interaction versus like if the ethyl was here, if this was an ethyl instead, right? There'd be no interaction there because they're far enough away from each other, right?
Yeah, so then, but like on page 12, to that point, why is it that I'm kind of in the middle of the page where
yeah,
yeah, so the ethyl has an arrow that says it's like has an interaction with both of the hydrogens, but each of the hydrogens are 2 carbons away.
yes, I am. Oh, right here.
Yeah, so
It's this one,
is
correct? This is what you're talking about?
yeah, that's the one. Is it just because they're all axial?
Yeah, they're all axial. And then remember we were talking about this, and this was something I often forgot about, is like just to make sure that like these 1,3 diaxial interactions, right? So that's literally, it's just like a little rule that you just have to know. So, and this is why. Here's 1, here's 3. They're axial, and they're all, remember that the way that the chair is shaped is this right here, you have, right, we have this shape to it. And so these are all kind of pointing up. These pieces are all pointing up. So even though they're every other, those ones are all within the same plane. You could say, you could argue that there's this plane right here that's running that has these all on it. And then there's a second plane, you could argue that there's a second plane directly underneath it that carries these carbons, right? And these carbons are all on that plane. And so this upper plane here, this blue plane here, that we'll just do a little bit of this to identify that it's on a different Z coordinate, is that, so all of these are in the same direction as one another, right? And so they're all moving upward, as we can see, they're all moving upward, and they're all on this like similar plane. So they have this, that's where this 1,3 interaction comes from. So, and that's why you have those diaxial, excuse me, 1,3 diaxial interactions. And
Yes,
so that's what, yeah, go ahead.
sorry, no, I was gonna say,
No,
so it's
right.
either 1 or 3, or they have to be directly next to each other and like both axial or like up or both axial down. Like those are the test cases.
Yeah, so there's right next to each other, like you said. There's not a lot of great examples right here close by, but yeah. So it'd be like, you know, if there's 2 equatorial, so this is pointing down. So if we had an equatorial here and an equatorial here, oh God, let's get these messed up, but whatever, you get what I'm trying to say, right? This would have some sort of interaction.
I
Or
thought
if
that I thought the equatorial didn't have any.
you would have equatorial, sorry, if you had your substituents next to each other, yeah, equatorial is the least energy. But even if you have, I want to see if there's an example on here. Even if you have them, they're still going to have some sort of like a gauche interaction, right? Like, so you can still have that even if they're on the equatorial. Remember, did I erase that example that we were talking about it, where I drew it out with like the different, remember, so even if they're next to each other, even if they're equatorial, they're still going to have some sort of oh, right here, remember?
Yeah, that's why I'm confused, because it says on page 12, top of the page, there are 2 gauche interactions in the axial conformation and 0 gauche interactions in the equatorial. But then on page 14, to your point at the bottom, then she's like, oh, they're both equatorial, but they have gauche. So how do you
Because at the top of 12, is that 12? Yeah, at the top of 12, the ones that are in your equatorial are hydrogens. So there is no interaction. But at the bottom of 14, the ones that are equatorial is a methyl and an ethyl.
Oh my gosh. I did not. Yeah, okay. I did not catch that. That is amazing.
Okay.
Thank you.
Yes, you're welcome. Yeah. So if the substituents are like not hydrogen, then yeah, you're still, if they're next to each other, you're still going to have Gauss interactions. But if they're hydrogen, then remember, hydrogen is our emotional support Pomeranian, right? Like it's fluffy in there and cool looking, but it doesn't really do too much. Right?
Yeah, I like completely didn't even notice.
No worries. No worries. Yeah, that's why we're here, right? That's why we're doing these things. So in our example right here, I have that, see, our hydrogens are these axial ones, right? And then these, the methyl and the ethyl are along our equatorial, but they're big, right? Versus the ones up here, how far up is it? Oh, boy. Oh yeah, versus the ones up here, these guys are so much closer. So even though this is hydrogen, ethyl is pretty long, right? Ethyl is a carbon here and a carbon here. And then there's all these hydrogens coming off of it, right? So it's got a hydrogen and a hydrogen, and this has got a hydrogen, a hydrogen, a hydrogen, right? And so this can spin and this can, kind of spin around like that, right? But so you're gonna have interactions. That's why there's always that the 1 to 3 are always gonna have that like Gauss interaction. I always forgot it, to be honest. So like, don't do what I did, right? And like further down, I didn't add it to it, but it says like, if you've got you just do like an ethyl methyl. If this is a ethyl, right? This is an ethyl, so that's why we would just do an ethyl ethyl. So it's just if it's in the axial, you'll just always add an ethyl methyl or whatever it is, isopropyl methyl, right? Gauss interaction into your KEQs or into your equations. I always forgot it until I got to the exam and then I remembered. But yeah, it was something that I had to commit to memory. So
Okay.
Yep. So axial, just add, if it's anything other than a hydrogen in your axial, make sure if they're on the same side, right? That's why they call it 1, 3, because they're on the same side, right? Just make sure to add your Gauss. Okay, what else? What else you guys got? What else do we have here? Let's see.
I have a comment. You're the
Yeah.
best TA probably in the universe.
Well, I don't know about that, but thank you so much. I appreciate it.
Because I will do well on this because of Sarah.
Yay!
Yeah, no, I'm literally looking at like the last page. Let's see if there's anything else. How do you know it's oh, just on the last page on 14 at the top-ish, like there's a methyl in the isopropyl, and they're making the distinction. It says important in bold. Do not make the mistake of drawing the wrong enantiomer. Yeah. And so what is the point they're trying to make here? Like, why is this?
Yeah, because what you're doing is you're changing your conformation. So that's what they're trying to say. So that's why I said whatever, let's just like pick, let me just draw this out, because this is a really important distinction and you will lose points. So what we have decided, so we are looking, let me just draw the eyeball in a different color. We'll do a blue-eyed girl. I don't know if you're blue-eyed, but we'll do blue-eyed today. But so we're looking at it in this direction. Front, not the same. I just want to make sure back. Yeah, so it's saying to look at it like this, right? And so the chair conformation that they gave is this. Okay, just Don't make fun of my chairs, okay? They're always horrible. They're never gonna look better. And then we have this. This is I'm doing it in bold like that to make the point that it is equatorial, not axial. Because it does get kind of funky, especially when you get these ones. Okay, so that's our isopropyl. And then, so what happens is the next one that they give us, ugh, it was like the bane of my existence drawing these chairs. Let me draw them a little more slanted so it's more obvious. Okay, slant. One. And then slant. Okay. Right. And then so what we've done now, and of course I'm at the edge of my page. Can I just move this? How does that work? Oh gosh, look at that. Oh my goodness. I'm a noob to good notes. So anyway, and so then now what we've done, this is still pointing up, right? This is still pointing up, but it's now, and this is pointing down. But this is now, this is axial, equatorial. Axial, equatorial, right? Is that right? Or the other way around, sorry. Axial, equatorial. Right, and so the point that they're trying to make is, so we see how we have this. I'm only caring because I want to make sure you guys understand. Okay, so what it's telling you not to do, which I'm going to draw in red. So what it's telling you not to do is to draw telling you not to draw this, because we are looking at it where this, let me get just a highlighter. We are looking at it where this is the front, right? And remember I had said before, and so this is the front. This is the front. So this is the back. Let me make sure I do this correct. This is the back. This is the back. This is the back, right? So it doesn't want you to do this because we have identified that the isopropyl is on the front. And as we can see here, it is on the front. It is on the front left of my green line. And on this one back here, it's on the back left, right? So that's what they're talking about. And then this would be the front here. Just want to make sure I draw that correctly. Okay, so this is what they're talking about. So if you are moving your chair around from here to here, you're flipping your chair, right? To say, remember, because the wedge means it's upward facing. So annoying. And the dash means that it's downward facing, right? And so here we have a downward axial or a downward equatorial. Here we have an upward axial or an upward equatorial, right? But we've made this distinction that we're looking at it so that our chair conformation has the isopropyl on the front side versus this, which is what they're saying not to do, has the isopropyl on the back side. So even though, yes, if you counted it 1, 2, 3, and you wanted to count this 1, 2, 3, because we've made this distinction that we want to look at it so that our isopropyl is on the front, we have to put it on the front. So 1, 2, 3, 1, 2, 3, right? Does that make sense?
I see that. Yeah, I didn't realize that the physical front of the, like, the hexagonal or the hexane one had to be the physical front of the chair.
Yeah,
I see
it
that
depends
now.
it depends on where you're looking from. In this
Yeah.
example, they're specifically saying that they're looking at it this way. So that makes the right side of this structure the front.
Yeah, got it. Thank you so much for going
Yeah.
through that.
Yeah, no problem. No problem. Anytime. Okay. I think we've gone through most of these pages, which is good. I'm happy to do so. Does anybody have any other questions? Any lingering last thoughts? I will take the silence as confidence. You guys are going to do amazing. You guys are going to be fine. I know this class goes really quickly, especially a 6 week. I'm doing biochemistry this semester, and I'm like, oh my God, what kind of psychosis must I have been in to sign up for this, right? So I'm sure you guys feel a little bit the same doing organic chemistry in 6 weeks, but you guys are going to do awesome. It's going to be a breeze. You guys are going to build. I forgot who asked me before, but Dr. Pillai is not teaching Chem 2. So for those of you going to Chem 2, she's not teaching it. So, but I don't know who will be teaching it.
Can I just ask, are you a chem major?
I'm not, no, I'm a pre-med biology major. I'm doing the accelerated program. So I'm in the